This video lecture is on Chapter 1, which is Introduction to Bioenergetics. To begin a discussion on bioenergetics, we must first talk about delta G. So G, or Gibbs free energy, is the free energy content of a closed system. Delta G is the Gibbs free energy change. It is the difference in energy when a system changes from an initial to a final state. Delta G is also the amount of energy available to do work. The important thing to remember is that if delta G of a reaction is negative, it is a favorable process. That is, energy is released and thus it is exergonic. If delta G is positive, then the reaction is unfavorable. This means that energy input is required and is endergonic. There are many equations for delta G. This is one of them, where delta G equals delta H minus T times delta S. So delta H is the enthalpy change of a reaction, or the heat change of a reaction. Delta S is the entropy change, so the change in disorder of a system. And T is the temperature in Kelvin, or K. Ultimately, this equation shows that changes in both enthalpy and entropy contribute to whether a reaction is favorable or unfavorable. So whether a reaction is favorable is related to delta G. Here is a mechanical example. So imagine there is a large cement block that's tied to a pulley and propped up on the top of an inclined hill. There's a natural tendency or potential for the block to slide down to the bottom position of the hill, which means there is a loss of potential energy when the block changes position, making it exergonic and the delta G less than 0 or negative. Imagine a different situation in which a small cement block is tied to a pulley and propped up at the bottom of an inclined hill. Work must be done to raise the block to the top of the hill, making it an endergonic process, and so the delta G will be greater than 0 or positive. Now imagine the situation where these two cement blocks are attached together. The loss of potential energy with change of position of the larger block can be used to provide the energy required to raise the smaller block up the hill. This is what we call energetic coupling, where a favorable process can be used to drive an unfavorable process forward. This is a common theme that we will see throughout the class as we examine biochemical reactions. Arguably, the most important molecule in biochemistry is adenosine triphosphate, or ATP. ATP is the energy currency in the cell and is used to drive many unfavorable reactions forward. This is because stored energy is released upon its hydrolysis. So let's go back to this idea of favorability of a reaction. So here's a chemical example. Imagine a reaction which is hydrolysis of ATP, where ATP is hydrolyzed to make ADP plus phosphate. This diagram shows the reaction coordinate on the x-axis and free energy on the y-axis. ATP has higher free energy compared to ADP and phosphate, making ATP hydrolysis an energetically favorable reaction, resulting in a negative delta G. In contrast, reacting glucose with phosphate to make glucose 6-phosphate requires energy and the delta G is positive. To make conversion of glucose plus phosphate to glucose 6-phosphate possible, this reaction can be coupled to ATP hydrolysis. In other words, the two reactions can combine into an overall reaction, and the delta G's can be summed together to yield an overall delta G that is net negative. In this class, we will see many similar reactions where the favorable hydrolysis of ATP is coupled to other reactions to make unfavorable processes favorable. One common theme that we will see in this class is the idea of entropy or disorder in the system. So the important thing to remember is that increasing disorder or entropy is favorable, whereas increasing order or loss of entropy is unfavorable. So imagine two desks, one with neat stacks of papers and the others with papers strewn all over it. The neat desk is more orderly and thus decreasing in entropy. The other desk is disorderly and thus is higher in entropy compared to the orderly desk. So similar to trying to keep a desk orderly, it is much easier or favorable to allow a desk to get messy. And so the idea is that increasing entropy is always a favorable process. This idea will become more important as we begin discussing hydrophobic interactions in biochemical molecules.